Okay, so hi everyone. My name is Avishag, and together with Dr. Einat Grimberg, Felix Tenner, and Professor Lanir from Haifa University, we are working on a research in the field of last mile delivery robot teleoperation. The research was funded by the ISTRC. So in the last decade, the volume of e-commerce was growing rapidly, and it is expected to continue to grow with 10% expected growth in annual growth in incomes, which means a growth of $6,500 billion by 2029. This will increase the amount of deliveries and thereby rise traffic levels, pollution, and also customer demands. Customers already today, they wanted their deliveries to arrive faster in more efficient way, which requires from us streamlining the supply chain. This can be done by using advanced technological means, such as autonomous vehicles. Already today, autonomous vehicles provide deliveries, and they do it in a relatively cheaper and faster and more effective way. Last mile delivery refers to the very last step of the delivery process, the step when the shipment goes from the local warehouse, from a big truck that brings a lot of deliveries, or from a local restaurant to the end customer. This is considered as the most expensive part of the entire shipment. It can reach up to 50% of the entire cost of the whole shipment. So how can we optimize the transfer of a single product or a few products from a restaurant or a local warehouse to the end customer without using expensive and cumbersome means of transportation? Or in other words, why deliver 2-pound burritos in 2-ton cars? So autonomous robots are a potential solution for last mile deliveries. There are two main options these days: drones and ground-based robots. Due to regulations and also weight and size limitations, the use of drones is not yet possible. And this opens the door for ground-based robots. So the idea is that these robots will perform the entire delivery process from the restaurant or the local warehouse to the end customer. Last mile delivery robots are revolutionizing the way goods reach our doorstep. And they do it, they're very efficient, but they also do it with a delightful futuristic flair. People really like them. They're really cool and cute. So imagine you're ordering some pizza or, I don't know, some toy from Amazon for your child, and this robot comes to your doorstep, winking at you, and you open it and you get your delivery. The idea is talking about 2 miles, the last 2 miles of the delivery. But they're not just really cool and fun and cute. They also have real advantages. They work without getting tired. They reduce delivery costs. And they're eco-friendly. They're cutting down on emissions compared to traditional vehicles. But they also have some disadvantages. And some of the disadvantages are that their autonomy is not perfect, and sometimes they encounter obstacles. That's why they will need a remote assistance from a human operator to help them overcome situations they can't overcome on their own. So we envision a future in which these robots are becoming widespread, with thousands of them penetrating our urban ecosystem. And therefore, a scalable and affordable teleoperation solution is essential. Very few studies examined last-mile delivery robots, and even fewer examined the teleoperation solution for them. And the ones they did, they were more technical, on the technical side. So we decided to unveil the challenges and use cases in which a last-mile delivery robot requires human assistance. And in order to do that, we contacted professionals, 15 experts from relevant fields, and conducted 15 in-depth interviews. All interviews were first transcribed, then they were coded by 2 coders, and finally analyzed using thematic analysis. So our findings revealed several main challenges and events that require or can be solved by teleoperation. First of all, these robots work on the cellular network. Sometimes the cellular network can become very loaded due to the use of cellular phones, IoT devices, and also autonomous vehicles and robots. And also, due to the urban environment that includes high buildings and very narrow streets, also underground passages, this can cause communication problems. And the robots can lose their communication and have trouble navigating. Sometimes they just stop in the middle of the street because they don't have way to communicate, and they just stop and interfere with traffic. Sometimes they lose their GPS signal, so they lose their position and can navigate. So these are problems that a remote operator can solve. Also, objects blocking the road, such as trash cans, parked vehicles on the sidewalk, fallen trees, and scooters can interfere with the robots in the way. So in the first stage, the robot will try to reroute and find a different path. But if he won't be able to do that, then a teledriver can take control of the robot and drive it. Robots can get stuck in sidewalk cracks and without being able to move forward, and also struggle with weather conditions such as rain and snow that can cause them to also get stuck or have problem with getting the road right. Also high changes like stairs. This is something that the robots today don't handle very well. And crossroads. Today, most of the companies, they have obligation to take control of the robot once he gets to a crosswalk. The robots can't cross the road on their own. In a few countries, this is like the regulation. They have to use a teledriver to cross the road. Also, technical and mechanical issues like broken engine, lid doesn't open, so people can't take their delivery. All kinds of parts that, like cameras, sensors, lights, they don't work. Low battery. These things can sometimes be solved by the teleoperator, and sometimes he will need to send a technical team to the robot physically to assist him. And finally, robots interact with pedestrians, dispatchers, receivers, drivers on the road. And these interactions can be positive or negative. Sometimes the robot itself is the obstacle, but it's very important for the robot companies that these robots will be accepted on the street. So it's very important that the robots won't become hazards for pedestrians. There are cases of vandalism. People just sometimes kick the robot, try to ride it, it really happens. People try to ride it. Homeless knows that there is food inside the robot, so they try to steal the food. But there are also positive intention communications. Sometimes the positive intention is it's still an obstacle for the robot because someone wants to interact with the robot and try to say hi and look what he will do if I will stand in front of him. But it's still, the robot is trying to deliver something, so it's still an obstacle. Sometimes these interactions are very positive. There are people that see a robot that fell down and actually come and pick him up. So in these situations, it's very nice and very good for the company that the robot will interact with this person. So usually they say something like, thank you very much, have a good day. So we'll see an example. This is a video of a guy that's following these robots. He has a TikTok channel filled with short videos of these robots. He knows them by name. Some of these robots have names. So he knows them by name, and he also knows them by their character. The character is actually the teledriver's character, but that's what he says. So we'll see an interaction. He met Juan. He knows Juan, the robot. He met him on the street. And let's see how he interacts with the robot and the teleoperator interacts back.
What are you doing now, Juan? What are you doing? Why are you trying to challenge me like this? What are you going to ram me? With those eyes. Menacing. All right, now you're trying to win me over, huh? I like you now. Juan, I'm going to tell you, you're my favorite robot. Even if you are a little crazy. You have that freedom to travel all over the city. Instead, you're delivering Starbucks to people. I guarantee the inside of that is full of coffee splashed all over the place. Looking like a crime scene.
So this was Juan the robot. So other than the obstacles and the challenges, we also found a few operation modes that teledrivers can use, that remote drivers can use. They already use it today. So the first is monitoring. When there's no specific case to operate, then the teledriver monitors a few robots at once. Usually, well, in the very small companies, it's actually one-on-one. It just monitors one robot. But there are companies when you monitor 3, 5, even 7 robots at once. In some companies, there is actually supervisor that all he does is supervising the robots. And if there's something that needs to be taken care of, he forwards it to the teledriver. The second mode is teleassistance, which means providing short, discrete commands to guide the robot. So there are a few options for teleassistance. This can be that the system offers a few options, and the teledriver just need to choose an option. Like, for instance, if the robot encounters some obstacle, the system can suggest to the teledriver to bypass it from the left or from the right, or maybe continue straight. Maybe it's just like a pound or a piece of paper. And the teledriver just selects the options, the correct option. It could be drawing a path on a map, drawing a new path, and just let the robot drive autonomously, but by the path that is drawn. It can be something that one of the companies called go, no go. So like just if the robot can go or not. They usually use it when he arrives crossroad. So the teleoperator takes control. Like the robot says, hi, I'm on a crossroad, please help me. The teleoperator takes control. He waits, see if there are no vehicles around, and says, go. You can go on. And there's also a mode of teledriving, which means physically, directly driving the robot. It is always better to solve the problems remotely, but sometimes it's impossible. So there's also an option that the teledriver sends a field team, like a technical team, to the robot to try and fix the problem where he's at, or pick him up and take him to the garage. So our future research plan is to design and evaluate a teleoperation interface based on our current research, which will provide research-based recommendations for designing a teleoperation interface in order to maximize the situational awareness of the teledrivers while minimizing their cognitive load and their performance time. That's it. Thank you.
Thank you. We have time for one question.
Define how many drivers do you need for a robot in an operation?
How many drivers do you need?
Yeah, to tele-support a fleet of robots.
Well, it's not something that we try to investigate and find the correct number, but different companies have different perceptions of how to operate this monitoring. You're talking about the monitoring, right?
Yes. Well, at some point you're monitoring, at some point you are driving. So
Sometimes the teledriver also monitors the robots when he's not handling specific situation. And then interviewees said that the average is about 3. There are also companies, like the big companies, they can handle 7. And the very small companies, it's 1-on-1. But there are also companies that have special function, which is a supervisor. He sits and he just supervises a few robots, and then it could also be 10 robots or more. And only if he sees something that needs to be handled, he transfers it to the teledriver. But the teledriver is kind of a higher position than the supervisor.
Thank you very much. Thank you.